I'm going to talk about the Etingof-Kazhdan quantization of bialgebras. I can tell you I'm by no means an expert in this kind of field, quantum groups and so on like this. 2 years ago when I said I'd give these lectures, it seemed like a really good idea that I should finally take the opportunity to learn about the Etingof-Kazhdan quantization. And in the last 2 or 3 weeks, I've regretted that thought enormously. There's quite a lot of stuff here. I want to give you some reference. So first of all, feel free to tell me there's better ways of doing some of these things, or make any comments you like. Please be kind to me, however. There's a series of papers by Etingof and Kazhdan, which are, believe it or not, quantization of bialgebras, and I counted 1 through 6. And the ones I'm really going to be interested in are 1 and 2, both of which are published in Selecta Mathematica. I'll give you the dates so you can see where we are. 1996 and 1998. Actually, I think the paper in the archive, which covers 1 and 2, is in some ways more helpful than 1 and 2. And for a reason I'll explain. When I come to it. What seems to have happened is that chapter 10 of the paper in the archive got took out of the published version and became paper 2 in the series. And I must say, I find it much easier to understand chapter 10 of the preprint than I do paper 2 of the series. The other thing which is really amusing about this is that there's some fantastic misprints in there, in this paper as published. The one I like best of all, as you see, the most complicated thing in the whole thing is getting a co-algebra, a co-product on a particular algebra. And the section where Etingof-Kazhdan does this in the printed version is headed the complication. I'm sure they mean the co-multiplication, but some typesetter thought. But it's perfect. The other thing is the heading where they discuss Manin triples, which is one of the key things. It's called main triples. So Manin is the main man, right? You know, he is the man. So there's some nice things about that. Sorry. There's also a paper by Gear, and this is about quantization of super Lie algebras, which I guess is perhaps more directly relevant to the kind of things we want to graded Lie algebras. And there's Etingof's book, Lectures on Quantum Groups. Etingof and, I'm sorry. And I thought, Schiffman. I'll just call it Quantum Groups. And also Christian Cassell's book, a book on context. So there's some background. Now I'm going to start at the beginning and actually tell you what Lie algebras are, and what quantization of Lie algebras should mean. I'm going to start at the beginning. So let's start off with Lie bialgebras. So what is a Lie bialgebra? First of all, I'm going to say we work over a field K of characteristic 0. Then a Lie bialgebra. I'm not very good at Gothic letters, by the way, so I call Lie algebras L. So a Lie bialgebra over K is, well, first of all, a Lie algebra Okay, so particularly it comes with a Lie algebra structure. Secondly, it's got a linear map gamma from L into L tensor L. So this is going to be, this thing, it tells you it's got a Lie bracket. This thing is going to be the co-bracket. And it's got to have two properties. The first condition is this. This is a gamma is a one cocycle on L with coefficients in this representation in L tensor L. I'll explain I'll explain in formulas what that means. So the first thing to say is, of course, that L is a representation of itself via the adjoint representation. Therefore, L tensor L is a representation in the usual way of L. And so the condition that it's one cocycle is this. So L acts on L tensor L as the tensor product of adjoint representations. And then the condition that's a one cocycle is to say that gamma of the Lie bracket of x and y is equal to add x tensor 1 plus 1 tensor add x. Oops. Applied to gamma of y minus add y tensor 1 acting on gamma of x. Okay, so that's just the cocycle condition for that's gamma of the bracket is x dot gamma of y minus y dot gamma of x, where y dot means the action of the Lie algebra on the tensor square of its adjoint representation. That's the first condition. And the second condition is B the dual of gamma, which is gamma star from L star tensor L star into L star, is a Lie bracket. So, for example, one of the things that means immediately is that the values of gamma takes place in the skew tensors. So I could have replaced L tensor L by the lambda 2 of L, but that makes no difference. Okay, so now where does this come from? The canonical example, the motivating example, is the notion of a Poisson Lie group. Let G be a Poisson Lie group. So this means that, of course, it's a Lie group, right? So you have a Poisson bracket. So you have on the smooth functions on G. So this is the usual thing, a skew symmetric bracket, which the usual Poisson bracket. I'm not going to go over that. And it's going to satisfy some compatibility between the group structure. There has to be some compatibility between the group structure and the Poisson bracket. And this is given by, if I take the bracket of Fg and evaluate it at xy, right? So the bracket of F and G, so F and G are in here, of course. Then this has to be, well, it's always awkward to write down these formulas, but I think this is the simplest way to write it down. F composed with left translation by x, G composed with left translation by x, evaluated at y, plus f composed right translation through y, a right translation through y, g composed right translation through y evaluated at x. Okay, so that's the you can write this out any way you like. I find that's the most convenient way to write that out. Okay, so that's the compatibility between the Poisson bracket and the group structure. I go up here. Now, remember that always you can describe this Poisson structure by the Poisson tensor. P, which is something in the second exterior power of the tangent bundle of G. And the relation between the tensor P and the bracket is this, that the bracket of Fg, the Poisson bracket of F and G, is, well, there's a pairing between df wedge dg P. This thing, this left-hand side, this left-hand side of this thing is in the second exterior power of the cotangent bundle. This thing is in the second exterior power of the tangent bundle. When I evaluate that on that, I get a function. And that's the relation between the Poisson tensor and the Poisson bracket. Okay. So in terms of this, in terms of the Poisson tensor, so in terms of P, this equation here, star says P of xy is, again, left translation through x P of y plus right translation through y P of x. Okay, so again, all this needs interpreting. Of course, this P of y is a point there, and I translate by x and the derivative of that, of course, in the tangent space. So that's another way of describing this compatibility for me. I'm going to give you a third way. Let's just see. Okay. I want to make a comment here. By the way, look, notice that however, whichever one of these two identities you use, you find the Poisson tensor at the identity is 0. Right? Now, therefore, this never comes from a symplectic structure. In a symplectic structure, you would always use the inner product, whether it's skew or whatever, to identify T with T dual. You cannot do that with this because this thing is actually the 0 tensor. Right? In fact, this thing never has constant rank. When you think of this Poisson tensor as an endomorphism of T of G, its rank can jump around all over the place. So there's nothing symplectic about this. Okay, now, so I've got to explain why it is that a Poisson Lie group, its Lie algebra, is a Lie bialgebra. So the bracket defines a Lie bracket. The Poisson bracket defines the Lie bracket on the dual L star, which is the dual of the Lie algebra. And again, I'll do this in two ways because it's so first, suppose I've got f and g, smooth functions on G, and I'll set xi for the df, the derivative of f at the identity, so that's in the dual. Eta is df at the identity, so that's in the dual of the Lie algebra. Okay, and now the bracket of xi and eta is defined to be, take the derivative of the Poisson bracket at the identity. The derivative of the Poisson bracket at the identity. Right. Right, so that's a new Lie algebra structure. Well, it's not a new Lie algebra, it's a Lie algebra structure. So this is Lie algebra structure. Okay. Yeah.
Do you have an example of the example that is a G that we are more or less familiar with?
Well, yeah. I mean, you could. I mean, you see, the Poisson tensor. I mean, the Poisson tensor has to satisfy a certain property. But take SL2R for example.
SL2R.
I mean, all you have to do is pick a particular kind of 2 tensor. So there are lots of examples.
Yeah.
Right, but there is a choice there, right? So. I'm now slightly regretting I didn't work out, write out notes on the example of SL2R, which would have been worth doing actually. And you can do it quite explicitly. But I'm not going to try and do it without notes. Right? I'm old enough to know that never works. So let me give you another way of thinking of this thing. You see, this thing. So there's another way of thinking of this. Using right translation. To trivialize the tangent bundle of G, I can think of the Poisson tensor. P will generate for me a function which I call little p from G into L tensor L. The Lie algebra tensor, the Lie algebra. The Poisson tensor, well, it's a wedge 2 of L, but forgive me for, it actually lies in wedge 2 of L, sitting inside L tensor L, but in particular, I'll put that. And then I can now describe the cocycle. Gamma is the derivative of P at the identity, which goes from L into, whoops. So that's the co-bracket, right? So I've said the same thing in a different way. I've constructed the co-bracket. Here I constructed the dual bracket, and here I've constructed the co-bracket. It's an easy exercise to see that those two are the same things. Okay. So there's the example. Now, next thing I've got to do is to tell you what we're trying to do. So I now want to talk about I want to talk about the quantized universal enveloping algebra. Now, it's sensible right at the beginning, I think. In the end, I did it over this. Should I do things properly? And in the end, I felt there was no sense in not doing it properly. And talking about the notion of topologically free modules over what I call K, which is ground-free K with this indeterminate, which is universally in this game called H, with the power series in this indeterminate H. So what I mean is that if we've got any module over K of H, so this is a way of this is a way of introducing a language which deals with the question of there's going to be some infinite sums of power series. And it's just a language for dealing with that in a kind of a clear, straightforward way. So if M is a K module, then of course you have the inverse system, the usual inverse system, M mod H to the N, N. And what I'm going to assume is that M hat is the inverse limit of M mod H to the N, M. And this is, so say M is a topological K module if M is M hat. So it's already complete in this topology, right? So this is just, I'm saying that it's complete in the H-added topology, right? I'm just saying it's complete in the H-added topology. And then topology. And then, topologically free, so there's a topological tensor product. M tensor N is by definition the completion right, is topologically free means that it's topologically isomorphic to power series, and we know that this tensor product with W of H is V tensor W power series in H. You see, it's straight away going to come about because I'm about to write down a Hopf algebra. Right? I'm about to write down a Hopf algebra, but literally the thing I write down is not a Hopf algebra. Right? It's only a Hopf algebra if you use this tensor product. Right? So it seems sensible to make that clear right at the beginning. Right? So that's what I mean by topologically free. So now what I'm going to say is we say H is a topological over K, which remember is this power series ring. If, well, it's got a product mu from H tensor H into H, and always when I write tensor, remember that I mean this completed tensor product, so you're allowing some infinite sums, a co-product delta from H into H tensor H, and this is where it's really different. This is where, because I've allowed infinite sums here, I'm not assuming this lies in any algebraic tensor product. Okay, so there may not literally be a Hopf algebra, right? It's only a Hopf algebra in this category. Unit co-unit epsilon from H into K and an antipode S from H into H. And I'm not going to write down the conditions these things have to satisfy, but that's the list of data, and it's the usual list of conditions for a Hopf algebra. Okay? So what do I mean now by, you see, well, so if H over K, then B equals H over, oh gosh, horrible notation, H times H. Right? This is an ordinary, this is a Hopf algebra. Over K, right? And then, of course, using the language of deformation theory, what one says is then H is a formal deformation of B. Okay, that's just what when we're doing deformation theory anyway. That's what a formal deformation is. Now, what I want to do is to talk about a quantized universal enveloping algebra for a Lie algebra is a formal deformation of the universal enveloping algebra of L. So it's one of these things, it's one of these topological Hopf algebras, and it has the property that when you take H mod this, you get the universal enveloping algebra of L. Okay. Now, there's an important point to make here, that actually, if you have a quantized universal enveloping algebra for L, you give L the structure of a Lie bialgebra. Okay? Oh God, I can't reach. Or I should have put one more. Actually, I should have put one more reference, by the way, when I started I started listing the references. And actually, this is a really good reference. It's the reference to Drinfeld's paper in the Berkeley International Congress of Mathematicians. You see many of the ideas explicitly and very clearly explained there. So that's an important reference which I should not have left out. So Drinfeld makes the observation there. For X and L, pick X tilde in this in H, right? H. So H is the formal deformation, okay? And then you write down so that X tilde equals X mod H. And then you do the obvious thing. You write down gamma of X is 1 over H so that's the co-commutator, right? In the Hopf algebra structure, that's the co-commutator in the big Hopf algebra. Right? That's the co-commutator in the big Hopf algebra. Of course, the commutator in the Hopf algebra U of L, well, every element in well, that's abelian. So the co-commutator is 0. So this thing is divisible by H. And now I've got to reduce this mod H. Okay, so there's a formula for a gamma, and this thing is gives L the structure of a Lie bialgebra. So if you quantize, you're going to end up with a Lie bialgebra. If you quantize according to this definition of quantizing, you're going to end up with a Lie bialgebra. So if you want to go the other way, you may as well start with a Lie bialgebra in order to do the quantization. That's really the logic. That's really the logic. Having seen this fact, you realize that if you're going to quantize anything functorially, canonically, nicely, the things you should quantize are not Lie algebras, but Lie bialgebras. Okay, so that's the problem. Can you quantize a Lie bialgebra? Given the Lie bialgebra, can you quantize it? And what does that mean? Can you construct a Hopf algebra H with the property that it's a formal deformation of the of the universal enveloping algebra, and the induced Lie bialgebra structure is the one you started with? So that's the question. Okay, now next thing I've got to do is to start to build up some of the background you need in order to do this, some of the structures you need in order to do this. So I've now got to talk about Manin triples. Well, what is a Manin triple, first of all? So a Manin triple is a Lie algebra. Well, let me write it. L plus L minus is a Lie algebra second thing is two subalgebras oh, sorry, I left out one. Let me erase this. The second thing I need to give is a non-degenerate inner product which I just write like this. And the second thing is two isotropic Lie subalgebras such that L is isomorphic to L plus direct sum L minus as vector spaces, not as algebras. Okay, so that's the data of a Manin triple. A Lie algebra, two subalgebras, and those two subalgebras have to be dual. Right? But in order to say they're dual, I have to choose an inner product.
This decomposition is compatible with scalar product?
Pardon?
This decomposition as a direct sum, is it compatible with the scalar product?
Yes. And this has to be dual. The bracket vanishes on this and on that. So the only way it can be non-degenerate is if this is dual to that in the bracket. Right? Well, actually, okay. So that's the definition of a Manin triple. Now, look, I just said it really, haven't I? Because look, this L minus, is going to be the dual of L plus in the bracket. So what have we got? Right? That has to be the case, otherwise it's not non-degenerate. So what have we got? We've got a Lie algebra, and we've got a Lie algebra structure on its dual, right? Because L minus is the dual of L plus. Well, that's not far from a Lie bialgebra. Well, it's the same thing as a Lie bialgebra. Okay, but I'm going to put in a put that in a. So I'll put this as a little proposition here. So let L mu gamma, right? So mu is meant to be the bracket, right? Mu. Gamma is co-bracket. Right? Be a Lie bialgebra. And L star, gamma star, mu star its dual, I didn't say so, but you can check just from the definitions that the dual of a Lie bialgebra is a Lie bialgebra. The bracket in the original algebra gives the co-bracket in the dual. Conversely, you just have to check the compatibility condition. Then there is a unique Lie algebra structure on L plus L star. I think I'm probably assuming things are finite dimensional secretly here, by the way, right? Otherwise, if I wasn't, I'd probably have to actually think about. I'd probably have work from the word go with topological vector spaces. So I think again for the duality conditions. So I'm probably assuming something is finite dimensional. Right? I've learned half the lesson of being careful about infinite sums. Right? You know, I've learned the lesson. It's necessary. That doesn't mean I've learned the lesson. I should therefore do it. Such that, what do I want to say? L star are subalgebras of D. I want to call this D, right? I'm going to now call this D. D stands for the double, right? D stands for the double. So I'm going to call L plus L star D. There's a unique Lie algebra structure on that, such that L and L star are subalgebras of G, and the canonical pairing on L plus L star. Just evaluate the function on just the evaluation pairing between those two is invariant. And the D. And this is a roundabout way of saying just do the obvious thing. This is a roundabout way of saying just do the obvious thing. You define proof the inner product. It's defined in the obvious way. Bracket of xy is 0. Bracket of xi eta equals 0. So that here x and y are in L. And the inner product of xi with x equals the inner product of x with xi, which is just xi evaluated on x. And I'll write down the formula too for the Lie bracket. The bracket of x and y is the bracket of x and y in L, right? So the bracket of xi and eta is the bracket of xi and eta in L dual. And the bracket of x and xi, I'll write it out. So this stands for the adjoint action of something in the dual Lie algebra on itself. The co-adjoint action. the coadjunct action of something in the Lie algebra on the dual. You know what I mean, right? Right. So this thing shows. This gives D the structure of a Lie bialgebra. So of a Lie algebra. Now this is the thing we're actually going to quantize. The quantization procedure is going to go like this. What I'm going to do is start with this thing. Start with this particular Lie algebra. Take its universal enveloping algebra, and using the fact that it's got this Lie algebra is basically L plus L star, I'm going to play some games with that and produce one of these topological Hopf algebras out of the structure of that. Then I'm going to say, how am I going to quantize L? Well, L, of course, L is sitting inside D. Therefore, the universal enveloping algebra of L is sitting inside the universal enveloping algebra of D. And what we're going to do is actually pick out a sub-Hopf algebra of this deformed thing, which produces a quantization of the Lie bialgebra, of this Lie bialgebra. But of course, in order to do the quantization, I've already made the point that if I'm going to do a quantization, that Manin tells us that, Drinfield tells us that we should have a Lie bialgebra structure, and this thing has into, okay, watch L tensor L. So this is, I take the gamma for L, a direct sum, and I've got to get a sign right, minus mu L dual. All right?
Are you still in the proof of your proposition? No, huh? You finished the proof of the
I finished the proof.
Yeah.
I finished the proof. In other words, I haven't finished the proof. But I'm not going to say any more about it. I'm neither going to prove that this is in the algebra structure, nor am I going to prove it's the unique one. So this thing has a Lie algebra structure like that. I think I'm just going to make the point that it has a Lie bialgebra structure for the moment. In fact, it's a special kind of Lie bialgebra. Let me at least say, I'm not going to write much about this because I want to start getting to some of the real meat of the construction. It's what's called a quasi-triangular Lie algebra structure, right? And I can say what that means. Remember that the Lie algebra structure was given by a cocycle. Okay. Well, what happens if that cocycle is a co-boundary? Well, that's a special kind of Lie bialgebra structure. And what happens if it is a co-boundary of satisfies some nice equation, which is called the classical Yang-Baxter equation, right? So it's saying that this is special. This Lie bialgebra structure is special because the cocycle which defines the Lie algebra structure is a co-boundary, and it's very special because it's a co-boundary of some special thing, right? So
you confirm that if you take the dual of D, it has not the same Lie bialgebra structure than.
Say again.
So there's two ways. It seems that the bialgebra structure you give is not the dual of the one given on the Lie algebra structure, right? Because you don't use the action in some sense.
This L plus L star has the Lie algebra structure given by those
Yes.
coordinates. And this bialgebra, this cocycle,
yes,
defines the bialgebra structure.
Okay. So if I'm dualizing this, it's not like taking L star plus L as a.
I think it is. I mean, there may be some sign involved there. No, I don't do it.
You don't use the adjunct.
What I'm using is the co-bracket of
Yes,
L
but only.
and the co-bracket on L star.
Yes, but not the interaction between L and L star.
I'm not understanding. I think the interaction between L and L star comes from the algebra structure of this. Right?
If we dualize the co-bracket on D, do we get a bracket on D? I think this is the question.
No.
And
No.
the answer is, she said that it's no, because there is no the adjoint action, something like
I'm not.
this. And the co-bracket and the bracket are not dual to each other. On D.
On D, the co-bracket and the bracket are not dual to each other. No. Oh, okay, I understand your question. Sorry, I beg your pardon. I just
So in some sense, you build two bialgebra from
Yes.
from this data,
Yes.
D and its dual.
Yes.
Why?
Okay. Sorry. Now we've got to get going. So what I want to do now is talk about associators and the Drinfeld category. So the whole point now is the whole point. Pierre, I'm not sure how much you talked about associators. Oh, never mind. How much did you talk about associators? I was way on mine.
Not enough, probably. So, sorry, I was asking Damien what the R matrix is.
The R matrix.
Is
So
it
the R matrix.
anything which looks like an R matrix?
The R matrix is some very simple thing. So the R matrix is the thing. What I have to say is this Lie bialgebra is a co-boundary. It's a co-boundary of something, and that something is the R matrix. And it's just something completely tautological.
Okay.
It's something completely tautological. Right. I think. What is the R matrix? It's effectively. That's right. It's effectively the identity map. It's effectively the identity map considered as an element of L tensor. Right? It's effectively the identity map, right? Considered as an element of L star tensor L.
So it's not really braided in a non-trivial way.
This is no. Well, these things are going to get braided right now. Okay, so
No,
I mean, so what I want to do now is to start to talk about associators in the Drinfeld category, because the way we're going to deform this Lie algebra, the algebra D, the way we can deform this D is to take the category of modules for D and deform that. And having deformed the category of modules, we're going to pick out an algebra so that the category of module, it's the usual kind of nonsense. Deform the category of modules rather than so associators. So I'm going to do it like this. I'm going to follow. I mean, I understand. There are different ways. I'm going to follow Etingof and Kazhdan pretty closely on this. So that Tn, well, on all this. Actually, it's quite interesting. I read around a bit, and there don't seem to be many different expositions of this. I couldn't find one. Where the details and order of the details were significantly perturbed at all. It seems to be a pretty straight line path through this. So everyone follows Etingof and Kazhdan. So let Tn, so this is be the algebra over K, generate, this is the infinitesimal braid algebra. And the relations Tij is Tji. Tij TLM is 0 if I, J, L, M are distinct. third relation is okay. Okay, so this is sometimes called the infinitesimal braid algebra, and sometimes people use this as a presentation of the Lie algebra, but I'm using it as a presentation of the universal enveloping algebra about Lie algebra. Right. So I mean that algebra. Actually, I hadn't realised how interesting this Lie algebra is. I really hadn't. For example, I discovered in reading something Benoit Fraisse wrote.
This is a Lie algebra or associative algebra?
Associative algebra. Right? It is the universal enveloping of the algebra of the corresponding Lie algebra, of course. Right? Because you're just using it's just tautology. But this Lie algebra, what Fraisse does is he says, take this Lie algebra, take its Chevalley-Eilenberg complex, right? So you make a differential gradient thing out of it. Then the homology of that is the homology of the braid groups. I didn't know that, right? Sorry, apologies for my ignorance, but when I saw it, my eyes almost fell out of my face. In fact, what's more, he actually proves, in fact, that the Chevalley-Eilenberg complex of that Lie algebra is quasi-isomorphic to the homology of the braid algebra. So there's a formality theorem there as well. So I was really taken aback by that. Now, there's all this business about putting subscripts and so on. And again, I think that it's good to be absolutely clear what that's about, because it completely baffles me sometimes when people just put subscripts down next to things, and you're supposed to attach some meaning. So let P1, Pn be disjoint subsets then there's a homomorphism rho P1 Pn from Tn into Tn. And this thing is defined by rho of P1 Pn of Tij is the sum over P in Pi, Q in Qj, TPQ. Okay. So, and then for what you do now is you say that then for any x in Tn,
Pj, not Qj. P sub j. There is no Qj.
Q in P.
It's Q in Pj.
New summation.
There's no Q.
sorry?
Instead of Q, put P.
Oh, sorry, I beg your pardon. Sorry. Sorry. So and then if I've got x in Tn, then I write x P1 Pn for have I got n's and n's mixed up? No, I think that's right. Pn. I've got them mixed up there. For rho P1. So that's what it means, putting subscripts on there.
For P, you include empty set too, right?
Excuse me?
P1, sometimes P1 or P2 might be empty set, okay?
Yeah.
Okay, sure.
Then you get 0, yeah.
Mm-hmm.
Yeah. Okay, so now let's see. I'm not quite. So I think I just have to do it as I do it. I'm going to write now down what an associator is in this language and the code. Yeah.
May I just ask a question? It seems that you're describing an opera structure. Yes. just Bruno will be happy.
I mean, one of the things I think I would like to do is the final session this afternoon have for discussing things like that, because there are many different points of view about this, and I think lots of people have different ideas, and I think it'd be good to have that discussion where people collect all these things together, right? Yeah. I mean, for example, the mysterious paper 2 of Etingof Kazhdan, I'm sure, is about props.
It is. Yes.
Right. Well, so when I say I'm sure, everyone who knows what a prop is sure. so I, as I said, I'd like to collect those discussions and things like that for this afternoon. For the moment, I want to kind of drive through the logic, the headings of the Etingof Kazhdan papers. Right, now, now I'm going to write down associators from this point of view. So I'm going to start with phi, something phi in T3, but power series over H. Okay, so then there's various relations I'll write down. Phi 1, 2, 3, 4. Okay, so that's the pentagon relation. And there.
So, sorry, T3 is what? Is the Lie algebra or the enveloping algebra?
It's the associative algebra generated by those, right? Perhaps I should. I mean, the point is, of course, that associative algebra is the enveloping algebra, the Lie algebra I've written down by the same presentation. But what I actually mean is the associative algebra. Okay. So the next thing I might do is like, oh god, I thought I was lifting it and it suddenly came out the wrong way. So I put B e to the h t12 over 2, and this is going to be in t2h. Okay, so I'm going to so that's the pentagon relation. I now want to write down the hexagon relations. And the hexagon relations of these. B1, 2, 3 is phi and the other one is this one. So these are so this thing is in T4, right? This relation is something in T4, right? And these relations are something in T3. And these are the hexagon relations. Okay? So, okay. So now take P in the completed the algebra on two variables x and y. Right? Complete the algebra on two variables x and y. And I form phi is e to the p ht12 ht13. And this thing is going to be known as T3H. And then so phi is called a Lie association if phi satisfies the hexagon and pentagon relations. And Drinfeld tells us there exists such a thing. And over the rationals. Drinfeld tells us there exists such a thing. And that's the input into Drinfeld's. I mean, when I've looked, I have to tell you, when I first looked at Etingof Kazhdan, I didn't even get as far as this part. Right. Some years ago, I didn't get as far as this part. So I found myself when I was writing this down, thinking, just God, how far the things have moved over 3 months. Anyway, there it is. There exists such a thing. Now. Right, okay, now, I think again, I'm not quite sure what order to do things in here. Okay, I'll do it. Okay. So now back to L be a finite dimension. Lie bialgebra with double So then there's a thing called the Casimir operator. So omega in S2D. And what this thing is, it's a Casimir element. Remember that D is equal to L plus L star as a vector space. So the Casimir element is some where of course, where Li is a basis for L, and L upper I is the dual basis for L star. Okay?
Why is that symmetric?
No.
I'm sorry, I'm lost. Why is that symmetric?
I think it's in the R matrix or something like this symmetrization.
I don't think I meant it to be symmetric, to be honest.
You see, it leaves in S2D. So
Yeah, I know, but I think that was just. I think I just mean just in D tensor D. Right?
but S2D is not S2D.
No.
You want to symmetrize that?
I think I just mean. I don't think I want it to be symmetric. I don't know why I said this. Should I? I'm being slightly insecure now.
I think omega should be the symmetrization of the R matrix, basically.
Oh, sorry. I've only written half of it, haven't I? I mean, yeah. It's the symmetrization of that. That's sorry. Yeah. My that's too deep. How do I put that? Symmetrized, right? Right? Sorry. Yeah, omega is the R matrix. Right? Omega is the R matrix, and the thing I want is the symmetrization of the R matrix, is the Kazhdan element. So I've got this usual thing of thinking of omega ij as the corresponding element in endomorphisms of V1 tensor V2 tensor V3. So what that means is omega 1, 2 just acts on V1 and V2 and leaves this fixed. Omega 1, 3 acts on V1 and V3 and leaves that one in the middle fixed, and so on. Right? Right? So let me say again what this notation. So if A is like that, I'll write it out. Omega is some alpha tensor beta. Omega 1, 2 tensor omega. Right? And well, omega, of course, acts on V in the way it does.
And what is VI, V2, V3?
Pardon?
What are VI, V2, and V3?
Sorry, I beg your pardon. V1, V2, and V3. Yeah. Okay. Let me. I've left out a chunk. I have to tell you what the category we're operating on is.
So the R representation.
Yeah. So let me say it properly. I've just left something out. All right. So now let M be the category with objects D-morphisms. But the morphisms HOM in M from U to V is going to be, well, of course, HOM but with H joined, with a form of power series in that. So the objects are just the representations, but the morphisms are power series of morphisms, right? Power series of morphisms of Lie algebras, right? So this is
Everything finite dimensional or topological or nothing?
I'm probably going to chicken out and say U and V are finite dimensional, but yeah, I'm going to chicken out and say
Eventually,
U.
you want to do some Tanaka style.
Yeah, I mean, if you, what you ought to do. I mean, I ought to have taken seriously the point that I should work with topological things from the outset. And in fact, in the end, Etingof and Kazhdan have to do that. A, to get something which is truly functorial, and B, to handle, for example, infinite dimensional examples, which they want to do. Right? So I've kind of taken a halfway house here, being honest at some points and not honest at other points. Well, right. So let's say this is a K of U, K of H, sorry, linear additive category. And what I'm going to do, is we would use the associator to make this in a highly non-trivial way. A braided monoidal category. That's what the object of this particular thing is. Okay, so okay, I'll keep that board. I'll come back. So I start off with V1. V2, V3 D modules. I think that again, of course, I think I really mean universal enveloping algebra of D modules, but they're the same thing. But they are of course the same thing, right? Then this starts to come in. So then I write omega ij in end. Okay, so there's my omega ij now. V1, V2, V3 are D modules, and omega ij is defined as it is here. Sorry, I left out some point there. And let's see what's next. Consider theta now from T3. Right, that's this thing over here. That's this infinitesimal braid algebra into
Sorry, so when you say omega ij and v, it means they are morphisms of modules, right? When you have the subscript.
Yeah. I think I'm getting the categories mixed. I'm getting the categories mixed up here, right? What I mean is, these are morphisms over D, right? Right. And I think here I mean n morphisms over n there. Okay. Right. You see, these things are endomorphisms of that D module. Mm-hmm. But now I'm mapping this big algebra here with a variable h in it, so I better map to endomorphisms of m of that. Okay. Okay. And now I define phi of B1, B2, B3 to be theta of phi. Okay, so now this phi is an endomorphism in this big category, right? Now this theta is an endomorphism in this big category. Okay, then this thing, well, so let's see what I'm going to define beta.
John? Sorry. Maybe want to say word about why theta is well defined. So why the relations are preserved?
You just have to check them, right?
No, but there are
Yeah.
not many relations.
There are not many relations.
The
You
only
just check them.
relation is really T12 plus T23
Yeah,
plus T13 is central.
Yeah.
So you only have that to check.
Well, you really need that omega is actually
Yeah.
in invariant elements.
Mm.
At some point, you have to use the fact that omega is invariant.
Yeah, I think that's in the relations, right?
Yeah.
Yeah, but I think I realised that I needed omega to be invariant.
You need
Right,
the
which is why I snuck that S in there. I did. I realised I needed it to be invariant, right, in order to check those relations. So, okay, beta B1, B2. It's going to be S composed E to the H omega over 2, right? So where S is switch factors. Right, where S is switch factors, okay? So out of this I've constructed a morphism in the category M from V1, V2, V3 to V1, V2, V3, and a morphism in the category M from V1 to V2. Right? So the theorem is this, and this is due to Drinfeld. Define make the category M into a braided monoidal category. Phi, of course, is the associated constraint. Phi V1, V2, V3 is this associative constraint. And beta, the commutative constraint. Okay, right, and of course, the diagrams. This one is the pentagonal diagram for symmetric monoidal categories. And the two other ones, the two hexagonal ones, are the hexagonal diagrams for a braided monoidal category. Okay, so using this as the associative isomorphism is from B1 tends to B2, right? It's the associative isomorphism from B1 tends to B2 tends to B3 to B1 tends to B2 tends to B3, and this is the symmetric, it's the commutative constraint. These things make this category into a braided monoidal category. Okay, actually that's a natural place for me to stop. Right? It's a natural place for me to stop. Right? The point to make is that what I've done. The point to make is just stand back and think. What I've done is take this category. The category here is the category of representations of this D, of this the algebra D. I've blown up the category by this power series thing. And then you can actually think of this as simply saying, and I think this is the way some people would present an associator. Let's just write down formally something of this form, something of this form, right? When does that? When do those formulas give you a braided monoidal structure on this category? The answer is if and only if they satisfy the hexagon relations and the pentagon relation, right? It's just a formal thing you write down. You write down the diagrams and put in carefully all the isomorphisms. then these are then this pentagon relation and the hexagon relations are exactly the properties that thing has to satisfy in order that it defines a braided monoidal category. Okay, and that's just formal. What the non-formal thing is there exists one. But anyway, once we've got what exists, we've found, and I think you really should think of what I've just done as a quantization of the category of D modules. Evidently, if I put H is if I work mod H, right? If I work mod H, you find the old category back again. So what I've done is deform the category of modules.
With its usual symmetry.
Sorry?
With its usual symmetry.
With its usual symmetric monoidal structure.
monoid-
With its usual symmetric. I've deformed the symmetric monoidal category. That's it, exactly. I've made a formal deformation of the symmetric monoidal category. And an associator is exactly what you need to do, right? An associator is exactly what you need in order to make that deformation. Such an associator exists, full stop. Okay. I stop there. Return after lunch. Question? Go on.
What happens if you integrate a Lie by a finite dimensional Lie by algebra?
If you integrate a finite,
If you integrate its Lie algebra part into a Lie group, does it always define a? Can you always do that and define a?
I think the problem is you can't deform Lie groups. I think virtually the opening sentences of Grunfeld's article in the ICM are unfortunately you can't deform Lie groups, so you want to pass to a more flexible category which you can deform.
Can you integrate Lie by? I asked.
Can you integrate Lie by algebra?
You anticipated my next question because my first question was, can you integrate the Lie by algebra?
I suppose you can.
No, but it's more to say that there is actually an equivalence of categories between the Lie algebras of unipotent groups and unipotent groups.
Yeah.
So everything we do here is unipotent. So there's really an equivalent of categories.
I should know. I knew this. I knew.
I know you
question
know.
years ago, but I forget these things. But
So yes, in the
what is your answer?
The answer is that there is an equivalence of category between Lie by algebras and Poisson Lie group, such that the underlying Lie group is connected and situ connected.
So it does work.
So
Yeah,
that,
I think
one can integrate Lie by algebra.
Well, I will think about my next question.
When you say associator, you assume that this should be the exponential of Lie series, right? Yeah, so in this theorem, I think you don't need this condition, right?
Oh, you mean? Yeah. No, I'm saying I've chosen an associator, the associator.
So you mean that you don't assume the exponential of Lie series, right?
I assume this is the exponential Lie series.
But for this theorem, you don't need these conditions. Just assume
I think
that is the hexagon.
Yeah, I guess. Yeah. But yeah. But I want to start with one, right? Right.
So you picked the Casimir element, but you can imagine that you pick a more general element like an R matrix. So how does it interfere in the theorem? And this omega is really
I think so far anyone would do it. I don't think you need to say. You need to pick an R matrix, right? You need to pick a Casimir operator, but I don't think you need anything special about the Casimir operator apart from that, right? You will at some point. At this stage, I don't think. At some point or other, you will, right? But not yet. Okay? So we start again at 2.